Well, this is the third and final video of this one problem. We have gone on ahead in the other two videos and found the equivalent resistance of the whole circuit. And then we went on in the next video and found the voltage drop in current through each resistor. So we have a huge amount of information, and we are ready to at last make a statement about the power consumption of this circuit. Starting off with our basic equation for power, we can say that power equals current I times voltage V. Maybe you don't happen to have current and voltage, and you only happen to have maybe, let's say, voltage and resistance. Well, no problem. You can still calculate power even without having current. The way that we do this is using Ohm's law. If you solve for I in Ohm's law, you get I equals V over R. Let's plug that in for I in our power equation. This will give us P equals V over R times V. So all we did was we solve for I, which is V over R, and then now we just go on ahead and multiply by V. And this will give us power equals voltage squared divided by resistance. Beautiful. Lastly, maybe we don't have voltage, so we can solve with just current and resistance. So we'll say that power now equals current times voltage, but wait a minute, we don't have voltage. But we look up at Ohm's law and we see that voltage equals current times resistance. So then we'll just multiply current times resistance, which equals I squared R. So now we've got three wonderful equations: P equals IV, V squared over R, or I squared R. So if you have any two of those pieces of information, you are able to calculate power. Of course, in our example, we went through in all the gory detail and calculated every bit of information that we could squeeze out of this problem. So you can really use any one of your favorite equations that you'd like in this problem to calculate the power. It's a valuable exercise to just go through and use them. Make sure that you know how to use a calculator and that you're familiar with them. But I will go on ahead and give you the numbers right now. So for R1, this 200 ohm resistor here, you should get a power of about 0.1922 watts. Over here at resistor 2, the power should be about 0.0144 watts. Resistor 3 down here is 0.01008 watts. Resistor 4 is going to be 0.11532 watts. And lastly, resistor 5 here in the middle should be about 0.0393 watts. So now we can find the power of each one. You'd be able to rank them. Let's say if these weren't just resistors, but maybe they were light bulbs. One would have a 200 ohm resistor, one would have a 100 ohm resistor. You could go through and compare the wattages and thus say a statement about the brightnesses. So whichever one is putting out a lot of wattage would be a lot of brightness, and the one that's a little bit dimmer would be really low wattage. If you add all these numbers up, you might just get a certain special value. Putting these all into the calculator, I find that it is about, we'll say power total equals 0.37 watts. So add it all up, we're expending about a little over a third of a watt. I want you to look at something real slick, though. It's a little shortcut. Is that our last slide right here, where we reduce down our circuit to a 12-volt source and a 386 ohm resistor. What's the power consumption of this circuit? Well, you would assume that it'd be the exact same thing. Of course, we went and calculated current, so you can use any one of these three bits of information. Let's just use voltage and resistance though. So our equation was P equals V squared over R. So plugging in 12 volts and squaring, we get 144 volts divided by 386.8 ohms. And what does that magically equal? 0.37 watts. All right, if you have any questions, feel free to shoot me an email or drop by. Good luck.